This video will tackle one of the topics in our lesson 4, and that's the fundamental theorem of calculus. There's actually two fundamental theorems, and this video will cover the first fundamental theorem. And that deals with the idea that when we add limits of integration to an integral, that somehow this turns us from an indefinite integral into a definite integral, and that gives us this expression you see on the front page of our notes, f of b minus f of a. So we should have a little bit of an understanding of exactly why it works that way. So let's just, for the moment, assume that we used a nice simple example. Let's say we let f of x equal, let's say, 4. So y equals 4, right? Well, what do we know about that graph, right? Well, the graph of y equals 4 is simply a horizontal line at 4. And let's go further. Let's suppose that we were asked to find the integral of 4, and that we were asked to find that value from 1 to 3. So let's add a little bit of detail to our graph here, right? So we're only going from 1 to 3. So boom, boom, boom right here, right? So basically what they're asking us for is the area of this segment. So let's start with what we know. We already know that if we were to do geometrically the area here, that it would give us an area of 8. So no surprise there. The question is, well, why does it work that way, right? And we'll deal with some calculus here that says, well, you're allowed to integrate, and that's how you get from lowercase f, let's say, to uppercase f, right? But then it's saying basically just plug in the top limit, plug in the bottom limit, and subtract, and you get 8. So I know some of you are going to be more concerned with the why does it work that way. So here's an area explanation based off of some properties, right? One of the properties we talked about was the idea that the integral from 1 to 3 of 4 is the exact same thing, right, as the integral of 0 to 3, right, minus the integral from 0 to 1. So let's look at those areas, right? It turns out that the area from 0 to 3 winds up being 12, right? Rectangle 3 by 4 width. The area from 0 to 1 is just 4. And if you take a look at these, compare these to our answer, you'll notice that the key is, how would I get 8 from all that? Well, you would simply subtract. So it's really this area of a larger portion minus the area of a smaller portion, and that's leading us to 8. So this first fundamental theorem is going to be helpful for us in obtaining a numerical value for any of the integrals we want to deal with. So let's look at some of the first couple examples. I'm going to work on example 1, and then I'll give you the answers to examples 2, 3, 4, and 5. And then we'll come back and I'll work on example 6 in this video as well. So let's start with example 1, right? It asks, what is the value of the integral from 1 to 9 of 1 over square root of x dx? And so obviously if we know we're about to integrate this, we want to make it a little bit more user-friendly. So we're going to integrate from 1 to 9 x, right, to the negative 1/2. And that leads us to an integral of x to the positive 1/2, right? Add 1, divide by the new power. Clean it up a little bit. Let's call it 2 radical x. And then these limits we know are necessary here in this case, right? So we have to evaluate this function from 1 to 9. Remember, 9 is always, the top value represents b on the interval. The bottom limit represents a. So to finish up, right, it'll just be 2 square root of 9 minus 2 square root of 1. And when all is said and done there, we should get 4. So I'm hoping that that one example gives you enough guidance to work with the next 4, 2, 3, 4, and 5. So pause the video, go ahead and play with the next 4 examples, and then when you replay the video or when you pick up, I will have the answers waiting for you. And of course, as always, we could talk about anything that you don't seem to understand in class. I'd be happy to answer any questions. Okay, so example 2 should have gotten 4/3. Example 3 should have gotten negative 2/3. Example 4 should have gotten an even 14. And example 5 should have gotten 1. Let's take a look at example 6. Example 6 is unique for a lot of different reasons. Let's start with, what the original problem says here. Let's integrate from 1 to 3 the integral of the absolute value of x squared minus 4. So the problem with this is not only does this probably not fall into a nice, easy, convenient geometric category, but we have a bigger problem, and that is without the geometry, we don't know how to integrate a function like this. So this is where some of that prerequisite knowledge comes in handy. Let's look at the graph of this, right? Here's what's happening. On its own, right, x squared minus 4 is going to have two zeros, 2 and negative 2. And it's going to have a y-intercept of 4. My pen's acting up a little bit here. So it's a basic parabola running through negative 4, right? Well, think about what the absolute value means. The absolute value means that any piece that would have been negative is turned into positive. So this yellow graph I'm drawing right here, this W, if you will, that is really the graph we're looking at. They would like us to integrate that from 1 to 3. So the next hurdle we have is we have to recognize that part of this graph is like this upside down parabola looking piece, and part of it is just kind of this other kind of like disjointed piece off to the right of 2 here. So we actually have two different areas we're concerned with. So what if we had to do this by hand, right? What if we had to work through this thing by hand? Well, really what we have to understand is that this is a piecewise function. One of the pieces, it's actually 3 pieces when you think about it. But just for simplicity's sake here, right? One of the pieces we need to be concerned about is the upside down parabola. So that would be negative x squared plus 4, which is only valid between negative 2 to 2. Oops. No, that's going to keep happening. So negative 2 to 2. And the other function is actually x squared minus 4 as written, but that function is valid in the case we need it from 2 to infinity. And obviously it could also be invalid for negative infinity to negative 2, but we just didn't need that case. So technically, here's the deal. We're going to have to set up 2 different and distinct integrals here. One of the integrals will be the integral from 1 to 2 of that negative x squared plus 4 portion. We're going to have to add to that the integral from 2 to 3 of the regular x squared minus 4 piece. So again, you can kind of pause if you like here and work it out yourself, but what should happen is you should wind up getting 5/3 for this first area and 7/3 for this next area. Put those together and you actually get an even 4. Comes out nice. Now, right below this, you have a using the calculator section, and I actually referred back to, in the calculator, example 4, and that's what I'm putting in the calculator, trying to show you kind of what we would have to do to put this in the calculator, because you would have to know how to do this, specifically if they gave you something like maybe example 6, where you weren't expected to do it by hand. And so what I did for you is I actually worked through example 7 using solely the calculator. So I did not do this by hand because you don't know how to integrate this. In fact, there's no easy way to do it. So practice putting that in, pause the video, and then we'll regroup and make sure we get the same answer. So for example 7, I had the calculator give me an answer of 10.641. So just kind of make sure you got that. If you're not getting that, either you're typing it in incorrectly, or maybe you're in degree mode when you should be in radian mode, since you're dealing with cosine. All right, the final example, let's deal with example 8 here. It says find the area of the region bounded by this graph. Again, just so helpful to think about this in just pre-calculus terms. So if you look carefully, it's a cubic graph, right? And you can even rewrite this thing maybe a little bit as 1/4 x cubed plus 1/2. Now, at the very least, maybe that gives you an idea that when you graph that thing, it's kind of like a wider cubic function that passes through a half, right? And I don't even need this thing to be accurate for me just to understand kind of what's happening. That's really what I'm concerned with here. So they're asking me to find the area bounded by this curve, the line x equals 0, which is the y-axis, and then the line x equals 2 right here, right? And then, of course, the y-axis is, or the x-axis as well. So this little shaded region in here. So what we're concerned about is setting up this integral and then, obviously integrating and doing the problem correctly. So we're looking at the integral from 0 to 2. I'm actually going to pull out the 1/4 here. Treat that like a constant, right? Make that a little bit easier on myself. And when all is said and done here, you should get a final area of 2. So the next video you're going to want to watch follows up to this is just on average value, a little shorter, but a very different topic, although it involves integration and fundamental theorem as well. So I hope this video has been helpful.